My name is Gargi Sadalgekar, and I am part of the Robotics Institute Summer Scholars Program. This summer, I worked on developing a method for path optimization for autonomous rough terrain traversal. Robots with the ability to traverse extremely rough terrain have a wide variety of uses, such as terrain exploration, environmental monitoring, and search and rescue missions. A key requirement of many of these applications is that the robot is capable of traveling to a designated point using the most efficient path possible. However, determining the optimal path for a robot when traversing rough terrain is a complicated task. Over rough terrain, the robot's dynamics become non-deterministic, making it difficult to calculate which sequence of actions is the least expensive when trying to reach a desired location. Furthermore, the non-linear nature of the dynamics means that traditional linear-based controllers cannot be used, as they perform poorly when used on non-linear systems. An alternative form of control that can be applied is modeled predictive control, or MPC, where a model of the system is used first to predict the motion of a robot when given a sequence of actions, and then to continually recompute the optimal action sequence as the robot diverges from the predicted motion. Since the system's dynamics are non-deterministic, a Markovian decision process, or MDP, can be used as the model, and the optimal path can then be determined by solving the MDP problem. Unfortunately, traditional methods for solving MDP problems are too slow and computationally expensive to be used for model predictive control, which requires fast computation. My project deals with developing a new, faster method for solving the MDP problem and computing the optimal action sequence to reach a designated goal, using a sampling-based optimizer called the cross-entropy, or CE, method. The method starts by randomly sampling paths from a probability distribution and simulating each path using a probabilistic motion model. As shown in iteration 1, the first set of samples taken includes many suboptimal paths. In order to quantify the performance of each path, we use a cost function to evaluate each sample. Then, the samples with the lowest associated costs are used to reweight the sampling distribution, and a new set of samples is taken. As this process is repeated, the samples taken in each iteration become less costly and start to converge on the optimal path. A large contributor to the success of the algorithm is the type of cost function used to evaluate each sample. I tested two different cost functions in a flat terrain environment to see which one produced a more optimal path. The first cost function only evaluates each path based on the distance from the target to the robot's final position on the path. The second cost function evaluates each path based on the distance from the target and the overall path length. I found that the first cost function produced optimal paths that were accurate in reaching the goal, but were often too long and sent the robot on tangents that led away from the target, as shown in the image on the left. The second cost function was more effective in determining the most optimal path, as it produced paths that were significantly shorter and smoother, as shown in the image on the right. So going forward, what I would like to do is first test these cost functions on a rough terrain environment to ensure that they work in complicated environments. Then I would like to implement a multivariate Gaussian mixture model as the probability distribution that I use to select samples. I would also like to develop a cost function that minimizes the number of steps taken to reach the goal, as this is a common criteria in efficient path planning. And finally, I would like to compare the effectiveness of this method to other established methods to see if it is actually faster to use. So once again, thank you for listening, and thank you to all the sponsors that made this program possible.